All right, let's talk databases. If you've ever worked with one, I'm willing to bet you felt that pain. That moment when one tiny change creates this ripple of errors, and suddenly you just don't trust your own data anymore. Well, today we are talking about the cure, normalization. This is the process that turns data chaos into a clean, reliable, and trustworthy structure. Let's get into it.
So what's on the menu for today? First, we're going to diagnose the disease, these sneaky little problems called modification anomalies. Then we'll walk through the treatment, the step-by-step journey to what's really the gold standard, Boyce-Codd normal form. We'll even check out a pro shortcut, weigh the real-world pros and cons, and, this is a big one, find out why sometimes the smartest move is to actually break the rules.
Okay, so before we jump into any solutions, we really have to get our heads around the problem. I mean, why do we even need to normalize in the first place? Well, the answer comes down to these three silent killers of data integrity known as modification anomalies.
Sound familiar? You go to make one simple change, and suddenly your data is a total mess. It's full of contradictions, or maybe even worse, you've accidentally wiped out information you desperately needed. Yeah, that's not just bad luck. That's actually a design flaw, a trap hiding in your database tables.
You know, take a look at this project assignment table. At first glance, it seems totally fine, right? But look a little closer. See all that hidden repetition? The employee's name and their rate are stored over and over again. The project's budget is repeated for every single person on that project. And every time we repeat data like this, we're basically setting a trap for our future selves. And that is where all the trouble starts.
Okay, so these problems, they come in three flavors. You've got insertion, update, and deletion anomalies. Let's break down exactly what each of these means using our little sample table here.
First up, the insertion anomaly. So let's say you just hired an awesome new developer. You've got her name, you know her hourly rate, but she hasn't been assigned to a project just yet. How do you add her to the system with this table design? Well, you can't, because project ID is part of the key, it cannot be null. Your table structure is literally preventing you from storing perfectly valid company information.
And then you have the update anomaly. An employee gets a raise, fantastic, but now you have to go on a scavenger hunt through your database to find every single row where they appear to change their rate. You miss just one of those rows and boom, your database is now telling you two different things. It's lying. You could easily send out a report or an invoice with the wrong rate all because of one little missed update. That is a huge risk.
And finally, we have the deletion anomaly. What happens if an employee is only working on one project and that project gets canceled? Well, when we delete that project row to clean things up, we don't just lose the assignment info, we lose the employee's name and their hourly rate too. Poof, they're gone. Their entire existence in this part of the database just vanishes.
Okay, so that's the mess. How in the world do we fix it? The solution is a really structured process called normalization. The best way to think about it is like a journey through a series of levels, or normal forms. Each one solves a very specific kind of problem. And our final destination is Boyce-Codd normal form, or BCNF for short.
Our first major stop on this journey is second normal form, 2NF. Now, this rule specifically targets tables that have a composite primary key. That's a key made up of two or more columns. And the rule is actually pretty simple. Every other column in that table has to depend on the entire key, not just a piece of it. The whole key has to be responsible for every piece of data.
Okay, let's look at a concrete example. In this before table, the key is the combination of student ID and activity. But look at activity fee. Does the fee depend on the student? No, it only depends on the activity. That's what we call a partial dependency, and it's exactly what 2NF is designed to kill. So the fix is to split the table. Now the activity fee lives in its own activity_fees table, where it depends on the whole key, which is just activity. Problem solved. We've hit 2NF.
Next up is third normal form, 3NF. This one tackles a different kind of sneaky problem called a transitive dependency. This is basically when one non-key column determines another non-key column. It's like a game of telephone in your data. 3NF steps in and says, nope, no games of telephone. Every non-key column has to report directly to the primary key, period.
Here's a textbook example. In the before table, the student ID determines the building someone lives in, and the building in turn determines the building fee. See the chain? Student ID to building to fee. That's a transitive dependency. And the fix? You guessed it, we break it up. We move building and building fee into their own table, and now both tables are in beautiful 3NF.
And that brings us to the main event, Boyce-Codd normal form, BCNF. It's a stronger, stricter version of 3NF, and honestly, the rule is just beautifully simple. A table is in BCNF if every single determinant, and a determinant is just anything that determines another column, is a candidate key for that table. That's it, no exceptions.
Now, here's where it gets a little subtle, because this table here is actually already in 3NF, but it's still not perfect. Take a look at the relationship between buyer and department. Let's say in our company, each buyer works for only one department. So if you know the buyer, you know the department. Buyer determines department. But is buyer a candidate key for the whole table? Nope. And that is a BCNF violation, which can still cause anomalies. So how do we fix it? Well, it's the same move we've been practicing. We decompose. We pull that problematic dependency out and create a new buyer department table just for it. The original table then links to it using the buyer column. Now, in each of these tables, every determinant is a candidate key. Both tables are in BCNF, and those sneaky, hidden anomalies are finally gone for good.
You know, that step-by-step process is awesome for learning, but when you're on the job, you often just want to get to the solution. So let's talk about the shortcut, a general strategy that takes you straight to BCNF.
Think of this as the professional's algorithm for a clean design. Step 1, you list out every single functional dependency you can find in your data. Step 2, you figure out all of the possible candidate keys. Now, step 3 is the crucial one. You go hunting for violations. Any dependency where the left side is not a candidate key is a problem. And for every problem you find, you just pull that dependency out into its own table, leaving the determinant behind as a foreign key to link them. That's it. It's a powerful, repeatable process.
Now, after all that, normalization sounds pretty perfect, right? But like any big engineering decision, it involves trade-offs. It is not always a magic bullet. So let's get real and look at the practical pros and cons. The trade-off is really fundamental. It's data purity versus performance. On one hand, yes, normalization gives you incredible data integrity. It wipes out those anomalies and cuts down on redundant data. But the price you pay is often complexity. Because your data is now spread across more tables, your database has to perform more joins to piece it back together. And all those joins can slow down your queries and make the code a bit harder to write.
So this all leads to a really important practical question. Are there times when we should intentionally not normalize our databases all the way to BCNF? And the answer is a resounding yes. Sometimes performance and simplicity just have to win out.
See, it all comes down to what your specific application needs the most. Are you building a data warehouse for analytics? Well, that's a read-only system, so modification anomalies aren't even a thing. Or maybe you're building a system where every microsecond counts. The performance hit from joining tables might be totally unacceptable. In cases like these, you might intentionally denormalize your data. You accept a little redundancy in exchange for raw speed. And that's not bad design. That is smart, pragmatic engineering. And that is our grand tour of database normalization, all the way to BCNF. If this helped clear things up for you, do me a favor and hit that like button, share it with anyone else who might find it useful, and of course, subscribe for more deep dives. So I'll leave you with this final thought to chew on. We strive for these ideals like BCNF, but is perfect design some kind of final destination we can arrive at? Or is it more of a powerful set of guidelines that help us navigate the constant trade-offs we have to make when we're building real-world, effective systems? Something to think about. Thanks for watching.